Hello everybody, welcome back. It's our last class before an extended Thanksgiving break. Hooray! I'll spend mine packing. Always looking forward to that. So just to update you on some scheduling stuff, for one brief shining moment in time, I believe I am caught up for grading. That will go away on Friday. So you should have your homework 3 revisions back if you submitted one. I've also updated the grades for quiz 5 and anything else that has come in since then, and then homework 5 is due on Friday. So is anyone having issues with their code or otherwise that they want to ask about for homework 5? Yes, sir. Yes. Yep, so that's my bad. What happened is that I am running the newest version of M+, which is 8.1, and the ones in this lab are 8.0. And between those two versions, they switched out WRMR for SRMR. You can ignore that, because WRMR was apparently replaced in part because it sucks, and since SRMR is not yet available widely enough, then I don't care. You can report RMSEA and CFI and call it good. Yes, that one is my bad. And now they're up to 8.2, even so it just keeps coming. Other questions? Please. Fair enough. So when I compare, when I run the model that was trained with the loading, so it's just like one loading for all of the items, do I compare models between that and the second model with an error covariance, or? Yes. Okay. Yeah, I think that would be reasonable. Okay. Yep. And I've had a few questions on that note. Folks who needed error covariances in WLSMV, but then were like, what do I do in ML? Is anyone having that issue? No one? Heather was. What'd you do, Heather? Or is your mouth full? Okay, good. All right. Yeah, you use a method factor. So that is the trick that was at the end of lecture 5, in case anyone needs to revisit this trick. Let me pull that up. Here it is. So in analysis estimation methods that involve some kind of covariance matrix, so straight up CFA or IFA with a limited information polychoric correlation matrix, you are allowed to refer to residual covariances directly. So the two items that you want their residuals to covary, you put a width in there and it estimates it. You can't do that in full information ML with IRT or IFA because there is no such thing as a residual within that framework. So instead, what you end up having to do is create another factor. So in this example on the right here, I'm calling it resfact. And it is loading, the two items that load on it are the two items for which I wanted a residual covariance. I fix their loadings to 1 to create a positive covariance. If you know that you need a negative covariance, you would flip it so that one of these loadings is -1, and you estimate its factor variance. Critically, this new method factor, or resfact as I'm calling it, cannot be correlated with any of your trait factors. Then it is defined as a residual, as a leftover. And that should fit equivalently as if you just put the residual covariance in directly. So this method factor option on the right you can do in any model. The one on the left you can only do in models where you're fitting something to a covariance matrix. All right. Other questions? The model on the right is a special case of what's going to be called a bifactor model, which we may get into today, but most likely not until the week after Thanksgiving. So others? All right. One thing that I've had a few questions about in specifying location parameters in CFA versus IFA, since we're going back and forth in this invariance unit trying to link the two. So just to review, in CFA, when you specify model parameters, such as in this example 7a that we had done, looking at multiple group invariance across men and women in a single factor of depression, the loading part looks the same, regardless of whether you are fitting a CFA model or an IFA model. And that will be true in most types of measurement models. The differences then come in with respect to the next two lines. So in this case, when you refer to an item in a bracket, you are referring to its intercept or a mean. If I were to type that line when trying to do an IFA, when using categorical R, what will happen? Any guesses? I know you figured this out. What happens? Yes, it will say, what? There's no intercepts in this model. These commands are not recognized or something. And yes, you got to put the $ sign in. What does a $ sign signify besides this is where the money is? Thresholds, yes. If you understand thresholds, someone will pay you. That's how I remember them. But yes, in the world of CFA, when you are fitting a linear effect of the factor in predicting the direct response, you have intercepts and you have residual variances. In IFA, when you are fitting an ordinal response model in which the factor linearly directly predicts the logit or the probit of the response instead, such as in this example we started, which is 7C. So when you invoke this categorical option, and you're using either WLSMV or ML, then the code changes to look like this with respect to the locations. You don't have intercepts anymore, you have thresholds. And you have as many thresholds as you have response options minus 1. So in this example, we have 4 response options per item. Therefore, each item has 3 thresholds. So $1, $2, and $3 indicate the shift between 0 versus 1, 2, 3, 0, 1 versus 2, 3, and 0, 1, 2 versus 3. It's a cumulative logit or probit model in this case. So you have to write these out if you want to be able to label them, to do invariance constraints or otherwise to do math on them. The other thing that is going to be new that I don't think we did before is that the residual variance here are referenced, they're fixed to 1. And in invariance modeling, after we hit the point of scalar invariance for IFA models, you actually can test the residual variances, as crazy as that sounds. So in this case, they have to be fixed to 1. That is what the parameterization equals theta means. It's like a probit model where the variance is fixed to 1 in both the reference group and the alternative group. So just to recap, in the world of CFA, you have intercepts and you have estimated residual variances. In the world of IFA, regardless of how you've estimated it, you have thresholds. So for instance here, these are thresholds. In the world of IFA, if you're using WLSMV, you have residual variances fixed to 1. In the world of IFA, if you're using ML, you have no such thing as residual variances. Do you want to see an Excel sheet, or do I say that again? Is that going to help? No? Say it again? Type it in Excel? Either? Both? Both? Okay, yes. It's tricky. It's tricky to fit a model that's right on time. It's tricky. How's that? Yes. Ask the YouTube, those of you who were not alive during the 80s. Still, I believe, one of the most popular rap songs of all time. Next to, what is that song called? Hip hop, a hip to the hip, hip hop, you don't stop rocking to the bang bang boogie, up jumps the boogie to the rhythm of the boogity beat. What's that song? Someone help me. No? You know what I'm talking about. Okay, well, hopefully I won't get a YouTube copyright violation for singing other people's songs badly. But, so if anyone's out there, leave me a comment, okay? Yeah. Subscribe to my channel. No, that's okay. Here's my my note-taking thing here. So model and estimator. There's my first. So I'm going to put slopes, and I'm going to put locations as sort of the generic term, and then residual variances. There we go. Those are our things here. God, that's going to bug me. I know the name of that song. It was in The Wedding Singer. Ellen Dow sang it. Like 80-year-old woman. You know? No? Okay. Thank you. Jesus. Yes, that's what it's called.
The Sugar Hill Gang, 79.
Yes. And they stole the guitar riff from Chick's Good Times, as I recall. There's some deep cuts for you. But anywho, back to the task at hand. CFA, IFA via WLSMV, and IFA via ML, or MML, as it's often called, marginal maximum likelihood. And so this one is ML. So how do we refer to the slopes or the loadings? It's just factor by items, right? And that is the case in all three. So when we have the type of IFA models that we are most frequently talking about, graded response type models or partial credit type models where you have one slope per item, it'll look like that. The exception is a nominal response, in which case there's as many slopes as there are thresholds. Locations, these are intercepts. And so there, it's bracket, item, like that. Here, they are thresholds. So it's item $1 up to item $, we'll say K-1 for the number of categories. But in practice, you would list them. So in this case, it would be like item 1, actually item $2, and so forth. That is the same down here. Let me do wrap text. There we go. Then comes residual variances. Refer to the item by itself, they're estimated, no constraints. WLSMV, it's item at 1. Hey, no, don't. It's not a web address, thank you. And nothing goes there because they don't exist. And if you try to write something down, it'll just say, that's not a thing in M+ language. So if you get an error message that says something like, this is not recognized or this is not valid, check to see that you haven't messed this up somehow. There. Does that help? Excellent. I'm going to add to this cell, it's the theta parameterization in particular that this is valid for, which is the only one we're using to make our lives easier. All right. Everybody got that down? If you want it anyway? All right. Tyler's like, nah, I knew this already. I don't need to write it down. I'm good. All right. So that will come into play today as we finish up invariance. So we've been talking about ways of testing invariance for CFA models, multiple group versions of it, as well as dependent versions, whether in the same model. We started just the end of last time moving into the IFA framework, talking a little bit about differential item functioning. So that's what it's called in the world of IRT, differential item functioning. That means measurement non-invariance, but it's the same type of question. Do the measurement model parameters that relate each item response to the trait work the same way in different groups of people? So for instance, if I have items measuring ability, then my latent ability should be the only reason I answer the questions the way I do. If I am likely to answer the question higher at the same level of ability because I'm a girl, or because I have a PhD, or because I have brown hair, or whatever, that's differential item functioning. There's something else besides ability that is predicting my response systematically. And that, in educational testing, is usually very bad. Those would be considered bias items, right? Certain types of people should not be more likely to get an item correct based on something other than ability. So it's big business in that context. And it's also relevant any time that you're interested in testing the properties of an instrument for use on a sample for which it was not designed. So people are constantly taking scales and adapting them to measure related things on slightly different people. How well does the scale work in that regard? So these are the questions that you would want to ask before you would feel confident in using it for its intended purpose. So in the world of IFA versus IRT, you can either test the A's and the B's, that's IRT software does that directly, or you can test the loadings and the thresholds. What M+ allows you to do directly is to test the loadings and the thresholds. So just to remind you why this matters, this is slide 29 out of lecture 7 to review the back and forth for these things. If you have theta variance, the factor variance that's 1, then the loading and the A are the same thing. So you can test the equality of the loadings across groups, and functionally that's the same thing as testing the equality of the A discrimination parameters in an IRT metric. Cool. Where the difference comes in is threshold versus B. So B is IRT item difficulty, is the amount of the trait that you need for a 50-50 shot at the higher response. Threshold is the logit of the lower response when theta equals 0 instead. They are algebraically related to each other. If theta mean is 0 and theta variance is 1, the latter part of this equation drops off, and B is the threshold divided by the loading. So what this means in practice is that you can have different B's even if your thresholds are invariant if your loadings are non-invariant. B is a combination of the two. And I believe that is the logic by which the mutanes, my husband, and other people suggest that you should test the loadings and the thresholds together at the same time. The alternative argument is that because A and the loading are synonymous, you can test the loadings separately. At that point, what would typically happen if a loading is non-invariant is what? What happens next if you kick out an item because its loading is non-invariant? Do you test it for scalar? Typically, no. So in that case, if A is different, you wouldn't go on and test the threshold anyway because it's already failed the loading test. So B can be different because of either or both of those things. And M+, what we are allowed direct access to is the loadings and the thresholds. And so we can test those for invariance and know that when you back convert them into A's and B's, then they may be different as a function of either of these things being non-invariant. And I'll show you an example of what that looks like, practically speaking, in our 7C example. So loadings and thresholds, that's what we're doing. Cool? Okay. Diff test. That's the other wrinkle that you have to remember when doing invariance testing using WLSMV in particular. There is no log likelihood anymore. what WLSMV is a limited information estimator. It first builds an estimated polychoric correlation matrix. It takes the contingency tables of every pair of response, tries to figure out what the correlation would be for the underlying bivariate distribution, and it plugs that correlation in as its H1 model. So it works from a correlation matrix and then estimates the CFA model to try and maximize the fit to that correlation matrix. So there's all this extra stuff going on behind the scenes in terms of the weighting. It tries harder to reproduce the polychoric correlations that are better estimated than the ones that are less well estimated. And that's where the mean invariance weighting thing comes in. It has to adjust the chi-square for that difference. So when you get your output for WLSMV, you don't get HO and you don't get H1 because this is not based on likelihood. Instead, what you get is the chi-square test of model fit that compares the HO and the H1 for you. But if you wanted to test whether this model that we fit is, say, worse than a two-factor model or something like that, we have to do the nested model comparison ourselves using their version of comparison that's known as diff test. So we have to save information from the bigger model and then refer to that information when estimating the smaller model. It reads it in and does the comparison, such as will be the case here shortly. So given that our configural model will be the biggest model, what does configural mean again? Do you remember? I'll give you two alternative multiple choice. All parameters get to be different across groups, or all parameters have to be the same across groups? Different, yeah. So this is our biggest model. In this example, we're looking at activities of daily living, 7 items, each with 4 response options. Across men as the reference group and women as the alternative group. Configural model lets everything be different between men and women, except for the structural parameters that we're needing to identify so that we have a scale. So mean 0, variance 1 for the latent trait in each group. They're not sharing a scale yet. They're completely on different scales. Likewise, residual variances are fixed to 1 in both groups. Each group gets its own set of factor loadings, 1 per item, and its own set of thresholds, 3 per item. And this model information is being saved right here under the Save Data option. You are to give the name of the command, which is diff test, equals, and then the name of the data set. You can name it whatever you want. It's a DAT file, though. I've named it configural because that's what we're testing. So I'm not doing any comparisons yet. I am saving this information for future comparisons. So this should be the best fitting model. From here, we're trying to place constraints on it to make it simpler and have it not fit worse. So according to RMSEA and CFI, this looks pretty good. So I think we're in good shape. I have written out here how the degrees of freedom are calculated. And I've made a picture here of the factor loadings. And I think this is about where we left off, more or less. So what we're looking for then in the next step is whether we can constrain the loadings to be equal and have the factor variance pick up the differences. It doesn't look like that's going to happen. Blue is higher on most of the items except for 3, which appears to be somewhat anomalous, right? 3 looks on the surface like it's way more discriminating in women than men. So that's foreshadowing what may happen next. So here's my model where everything is different. Loadings and thresholds. Factor mean, factor variance, and residual variances are all fixed for identification. Next step. Let's see if I can get this all on one page here. No, not that one. This page. There we go. There. Next step is metric, loadings. To do so, L1 to L7 shows up on the alternative model. That means it has to be the same as L1 to L7 at the top. In so doing, I estimate the factor variance for the alternative group. So it's picking up any differences in loadings now. In terms of doing the nested model comparison, I am doing two things here. At the top, number one, I am bringing in the information from the previous model into analysis. So it's saying, hey, take that stuff you just saved from the other run and bring it back in so we can use it for the comparison. At the same time, because I know I'm going to need more models after this one, I am saving the information from this model, and it's going to be called metric A, foreshadowing, because we'll need more letters as things break down. So bigger model first, smaller model second, which is how it always works in invariance testing when done this way. Then we get two chi-squares. The first one, chi-square test of model fit, is H1 versus HO. Does a single factor model fit worse than just letting the polychoric correlation matrix be whatever it wants? This is usually significant. It also gives us the contribution to the chi-square from each of our groups, which depends on misfit as well as relative sample size. But then here is the one we care about, as I noted in block bold letters above it. And this is me being nice. M+ will never tell you this directly. Chi-square test for difference testing. That's what dip test gives you when you put it in the analysis section. So this is the nested model comparison against the configural model. So I had 14 loadings before. Now I only have 7 because I made my groups share a loading. And I get down to 6 because I had to estimate a factor variance to do it. So that's where the degrees of freedom 6 comes from. Chi-square is 9, p-value is non-significant. Looks like it should be okay, but I'm testing 6 things at the same time, so I want to make sure that there's not any local problems that I would be overlooking in doing so. And sure enough, if I go down to the modification indices, they suggest that item 3 wants to have a different loading for men than it does for women. And the chi-square would improve by this much if I let that be the case. That also conforms to what we saw up here. Item 3 looks very different than the others. So I let that happen. Three things changed. Actually, just 2. L3A down here, I have freed the loading for item 3 in the alternative group by giving it a different label. So it's still called L3 up above, it's called L3A down below. You can call it whatever you want. Just develop a system that makes sense to you later on. The other thing that has changed is that I am saving the results of this reduced model as metric B instead of metric A, so that I can compare it back to configural. So now, with 5 degrees of freedom instead of 6, after freeing that loading, it is more non-significant, if I can say that, and there's no individual loadings identified as problematic, so I feel like I'm done. So what happened then, if we look at the output from this metric B model, which I would call partial metric invariance, is that all of the loadings are the same across groups, with the exception of 3, which is almost twice as big in the women. But the variance of the women is much smaller than it is in men. It's estimated at 0.6 relative to 1. Why are these numbers so big? Why do I have loadings of like 4 and 6? What metric are these in? Close. Probits, yes. Yes. Probit is logit divided by 1.7. Logits are scaled to have a residual variance of 3.29. Probits are scaled to have a residual variance of 1. So, but yes, they're in this sort of transformed space. Item 3 looks to be way more related to the trait in women than in men. What is item 3? Cooking. Keep in mind this is a sample of older adults who were born in like the late 1800s. So there's some generational things here. But keep that in the back of your mind as the story unfolds here. All right. With me so far? Yes, sir. No, it's, let me pull out what it was before, actually. I can answer that question. Oh, no, that's scalar, excuse me. 2A. So in the A model, where all the loadings are forced to be the same, the residual variance is still, 0.69. So stated differently, close that out of the way. I've got too many windows open here. In most cases, the blue bars are higher because the men have more variance. Their variance is 1, and the variance of the women is about 0.7. The exception is 3. So 3 is anomalous because it's more related despite the fact that women are less variable. But before I declare that 3 is a better item in women than men, can I say that because it's more related? Or do I need to finish that sentence? Remember, CFA, high loading is good for everybody, right? Because it's linear. A 1-unit change in the theta creates the same change in the response no matter where you are on the response. What happens to the shape of the loading in IRT-IFA? It's specific to a certain point. What's the shape, though? I'll do my walk like an Egyptian shape here. There, that's the right direction, right? Nonlinear, bendy, right? Ogivy, probity, logisticy. Any of those words? Shut-offy is another one I like. It's this way, right? Okay, it's this way. There, walk like an... No! I have no spatial reasoning whatsoever. Just as a side note, I am completely deficient in that area. This way? This way. I got it? There. Now we've got an upper asymptote and a lower asymptote. I'm a little IRT model, short and spout. No. Here is my handle. Here is my spout. No? Some of you either work with children or have them. When I get all steamed up, hear me shout, tip me over and pour me out. I'm a little IRT model. That's what I'm going to teach Huey. He'll be the hit of his kindergarten class. But yes, the slope is bendy, right? So when we say it's a better slope for women, ... for women who, at a certain point, right, it's the slope at the difficulty value. So that's what we have to know to interpret for whom is that item better. And why does Office constantly restart itself in the middle of my lecture? These are the questions that I want to know. It hates me. Stop it. Okay. So let's figure out then for whom, at what level of the trait, cooking is a way bigger indicator of physical ability of daily living for women than men. because the discriminations are local. They're good slopes at their difficulty values. So that's where we have to get to the rest of the model to figure that out. So we have metric invariance that's partial. So 6 out of 7, I'd call that good. At what point is 2 partial partial, where you would declare it game over? I don't know. There's not a hard and fast rule. Personally, I think 2/3 or 3/4, somewhere in there. Mathematically, you need 1. You can hang your scales together across groups with only 1 invariant item. Practically speaking, that is a terrible idea, but you can do it. 6 out of 7, I think, is pretty good. It's not that item 3 isn't related in one group, it's that it's more related in one group. So it still matters, it just matters more. So let's look at the thresholds and preview what we're going to find here. So in contrast to intercepts, in the world of CFA, how many intercepts does each item get? 1. So it's either invariant or not, right? Woo! Yes. Good to hear from the back. Thank you. How many thresholds does each item get now? If I have 4 response options. 3 or 4? If I have 4 response options. 3, yeah. Think of it this way. If I know the proportion of people who answered a 0, a proportion of people who answered a 1, and a proportion of people who answered a 2, I know how many answered 3 because they have to sum to 1. So you only need to have 3 to get to the 4th. And I have color-coded them for you. I have men versus women in the blue and shaded, same with the green and same with the yellow. These are in probits. Look at 3. Thresholds are scaled such that lower values are easier items. It is the logit of not being able to do it at a trait level of 0. Look at the difference between 3 here. For men, going from not being able to do it to, sometimes, whatever 0 to 1 is, I can't remember off the top of my head, is way harder than for women. Cooking is easier for women in this sample. Let's put it that way. Their threshold is much lower, ostensibly at the same level of the trait. We're going to control for trait differences in ability and see if this pattern still holds. Otherwise, if you look at the rest of the items, it looks like women have more difficulty doing these things. Their bars are higher, except for that one. In other words, if women have more difficulty, is it because they have lower ability? We don't know yet. That's the question. So once we control for factor differences in ability, do they have the same expected chance of being able to do each of these items at each of these levels of proficiency? So let's find out. Now here's a trick that saves you typing that I have deliberately avoided teaching you until this point so that you wouldn't inadvertently screw things up by invoking it. Item thresholds, all nicely labeled at the top. And several of you have found out the hard way what happens when an item doesn't have all possible responses filled out, right? You can't use this nice abbreviation. You have to list them out. That's annoying, isn't it? I agree. So M+ has decided to save you some typing if you know how to cheat the system. When you say model women, what you're actually listing are only the things that need to be different. So in this case, we listed the loadings, which means make them different, but then we went ahead and constrained them to be equal to the top. I could have just not listed anything, except for the one that I wanted to be different. But I have to define the factor. The thresholds, though, if I want to make them all the same, I take them away. So this is a full scalar invariance model by absence of anything here. Because if you don't put anything, it just borrows what it is from the model. When I want to have thresholds differ between groups, then I have to write them and refer to them. Yep. So right here, I'm labeling my thresholds for men. And I don't even actually need the labels so far. That's a default. If I do nothing, it estimates all possible thresholds. The way that this model and then model alternative works is that in the alternative group, if you don't refer to something, it is assumed invariant. So by not referring to the thresholds at all down here, hence the blank spot right here, I am making them invariant with far less typing. And because of this ambiguity in whether or not you would need to test loadings and thresholds separately, I went ahead and threw item 3 back in the mix. I'm going to see if I can constrain its thresholds anyway. So I am now saving scalar A from this model. I am referring back to metric B, which is the model we just finished, where all of the loadings are held invariant except for 3, and the factor variance is estimated. I am now constraining all the thresholds to be equal across groups, and in so doing, this right here, don't forget that, freeing the factor mean. I am saying the only reason that it looked like women's parameters were more difficult is because they have less ability, maybe. That's a testable hypothesis. That's what I'm asking right now. Is the factor mean difference responsible for those observed differences in women's thresholds? If the model fits not worse, the answer is yes. Those differences are a function of the factor and not otherwise. However, significant difference in model fit up to like the 5th decimal place. So yeah, no, it's not just about differences in ability. There's something else here that's gender specific. Let's figure out what it is. To the voodoo, modification indices. Now you're going to see some funny things here. You see the dollar signs, right? So what kind of model are we in relative to my the spreadsheet we built a little while ago? Which row are we in? 2, 3, or 4? We're in 3, right? So when we talk about locations, we should be talking about thresholds, right? Dollar signs. And to that end, M+ suggests specific dollar signs that are causing problems, such as the first threshold for item 3 and the last threshold for item 3. And it lists some other items as well, but then it also does this. No, that's not very effective. Stop it! There. It also does that. What is it talking about? A thing in a bracket without a dollar sign. What's that? An intercept or a mean, right? It wants us to free the intercepts that don't exist. Yeah. My only way I can rationalize this is that it's picking up on some sort of constant shift for all of the thresholds of an item. Like it wants to move the whole thing over as if there would be an intercept shift. So if you look at the specific thresholds it's naming, 3 is a problem, 1 and 3 are a problem for item 3, and item 3 is the biggest difference. and 3 wants to move one way, and -1 wants to move the other. The whole thing, it wants to just move. So even though it is going to suggest intercepts as things that can fix your model, you can't estimate them. Likewise, it's going to suggest a factor mean difference. We already let it have one. So this is just craziness, and thus the term voodoo. But what we can do is think about these two as being, well, yeah, we kind of saw this coming. Since 3's loading is very different, thresholds could be different because of that, so we'll go ahead and let item 3's thresholds be free. I have a note here at this point that I'm going to come back to, but I don't want to introduce that just yet. But it's one of my most popular random people emailing me from around the world questions, and so I had to add that for their sake. So now we're on to 3B, partial threshold invariance. So note what I've done here. In the women's model, I have added back in references to only the thresholds that I want to be different, those for item 3. I'm saving this as scalar B. I'm still comparing it back to metric B. Chi-square difference test, better, but still not there yet. Suggestions. Item 1, threshold 3 is the next to go. So we pick up item 1, threshold 3 down here. Scalar C. Heading in the right direction, not there yet. Item 2, threshold 3 looks like the next to go. Add it here, up to scalar D. Still not there yet. Now I'm at item 1, threshold 2. Scalar E. Pick that up. Pick that up. And finally, hooray. So yeah, if you're in the world of IFA invariance testing, this can take a while. Like I said, I've had students get up to like scalar X before in models with lots of items. It can go for a very long time. And it becomes even more data-driven the longer it goes. Unfortunately, there's not an easy way to resolve that. Okay. So we have partial scalar invariance. Let's take a look at what that means. Here's my solution. It looks like the factor mean for men is 0. The factor mean for women represents the factor mean difference. So it's minus 0.3. Which is significant. So women do look like they're less able. The thresholds then that are invariant, so the ones that are not in bold, that is the probit of answering the lower category, so 0 instead of 1, 2, 3, 0, 1 instead of 2, 3, 0, 1, 2 instead of 3, whichever one you're talking about, for somebody who has average ability. So in other words, for the items that are not in bold, doesn't matter if you're a man or a woman, your chances of doing well at this item are dictated by your ability. You have the same chance if you have the same level of ability. That is not the case for the items in bold. So if we look at item 2, actually item 1, excuse me, thresholds 2 and 3. So item 1, threshold 1 is invariant. Partly because there's hardly any people in that category. There were very few people who answered 0 for any of these items, so those thresholds are not going to be that well estimated, and there's not going to be a lot of power to detect differences between them. But as you move up higher in the items, more people answered those higher categories, and so we have a better chance of actually looking at invariance differences. So we're in negative space. So for women, item 1 is more negative in its threshold. Let's unpack what that means. Threshold is the chance of the lower category. So there's less of a chance of the lower category at the same level of ability. Stated more simply, the items are easier for women. The thresholds are lower. So the same item at the same latent level of ability at a factor score of 0, item 1 is easier for women. That's right. Women is the only reason I have right now. That's all I know. But it's either gender or whatever gender is related to. Item 1 is housework, cleaning and laundry. So I'm going to put forth a hypothesis. At some point, the men in the sample were like, you know what? If I do this badly, I won't have to do it anymore. I'm sorry, honey, I can't. I'm not good at cleaning. I'm sorry. So at the same latent level of ability, housework was easier for these women than for the men. You can't make this up. Like I said, this cohort is very old. Not saying that any of this is true anymore, but in this sample of 634 people, this is what happened. Likewise, item 2, threshold 3, is easier for women. And item 3, all of the thresholds are way easier for women. So I know item 3 was cooking. It's at the same level of ability. There's a much lower chance that a woman can't cook. So that means diagnostically, if you come across a woman in this cohort who can't cook, she has serious issues, because cooking is super easy, according to this group of people. Like me, I have serious issues. You heard of the freshman 15? When I went to college, I lived by myself in a house with like a bunch of other people, and I actually lost 15 pounds because I couldn't make myself anything but spaghetti, and I got very tired of that. So, yeah, that's my story. Okay, now for the tricky part. Up to this point, everything works the same as CFA. This is the point where it diverges. Residual variance invariance is possible to test in an IFA framework. To do it, though, you have to go one step backwards. So residual variances at this point so far have been fixed to 1 in both groups. Once you hit at least partial threshold invariance, scalar invariance, the residual variances in the alternative group can actually be estimated. They're not really residual variances, though, because we're still in this probit metric where the variance is fixed. All they are is a slop factor, basically, that catches any non-invariance in the other parameters, and there's room to estimate it. This is something that, in practice, I have seen blow up more frequently than it actually works. So I didn't ask you to do this in your homework. The next homework for invariance, which is going to be due, I moved it to the Monday after we come back for break. I think I forgot to mention that earlier. It was going to be due on the 30th, and I moved it to the 3rd. That way there's one more class day to be able to answer questions. I'm not going to ask you to do this. But if you ever wanted to know how to do it, I want you to know the order in which we do these things. So we have to take a step in the wrong direction. Rather than fixing things to be equal temporarily, we have to step backwards and let the residual variances be free. So we're not comparing anything to this model. We're just estimating a new model in which the residual variances for item 1 through 7 are estimated with the exception of 3. So in this model 4A, I cannot test the residual variance for item 3 because all 3 of its thresholds are free. It's not identified. Only for the items in which at least some of the thresholds are shared between groups can I estimate the residual variance in the alternative group. So this becomes my new baseline with which to compare the previous model in which they were fixed. So I'm saving this one as residual free A. I'm getting my fit. Here are the residual variances in the alternative group, except for 3 that's still fixed. And then now I use that free model as the comparison, as the bigger model, and I go back to the model in which they're fixed. So for consistency, I've relabeled this as residual fixed B. It is the same thing as scalar E. So I jumped one step ahead to free the residual variances that were possible, and now I'm going back to where I was to see if they need to be constrained, if they can be constrained. And just barely significant difference. Here's item 7 is the culprit. I switch it up so that now we're estimating the variance for only 7, and the difference is fine. And I tested the factor variance, and it was different, and so we leave it, and so then we're done. So in sum, we have a different amount of variance in the trait in women, much lower. We have a lower factor mean as well, and we have different thresholds. So I made some pictures to help us understand what is happening with these models. And I added a new page that gives some code to calculate the IRT versions, which I had not done previously. So this is new. So let me look at, let's pull this up. Just one second. Pull up the spreadsheet that goes with this example. Hopefully Office won't yell at me. Here we go. So because giant lists of numbers are hard to convey what's happening, I like pictures. So here's a picture that I made of the thresholds. It's color-coded. So the first threshold is the blue one. That's 0 versus 1, 2, 3. The second threshold is red, and the third is green. So they're constrained in order because this is a cumulative model. Within each threshold, the solid line is the reference group, which is men, and the dashed line is for women. So for the lines that are the green and the red where they're right on top of each other, those are invariant. The versions where you can see the dashed line come down, those are the parameters that are non-invariant, that are different. So you can see for item 3, cooking, all 3 of the thresholds are much lower for women. Thresholds indicate difficulty, therefore those items are much easier. There is a much lower chance of them getting a 0 if they have average levels of the trait. Say that again. There's a much lower chance of them answering 0 instead of 1, 2, 3 at average levels of the trait than men. Show of hands, how many are thinking, what? Raise them up. Yeah, no. What? Or you're thinking, how in the hell am I going to explain this to somebody? Right there with you. I hate thresholds. I like difficulties. So let's look at those. So here's what I did. I had to type out some more code. I have all of the thresholds for men, and then I wrote out all the thresholds for women, in which I added a W after the ones that are different. I used model constraint to calculate B values for men and B values for women. B is threshold divided by loading, where the do loops are used to save code where it's possible to. So in the men's group, we just go 1 through 7 for the discriminations, which are the same thing as the loading, so I included that here for completeness. The B values. And then in the women's group, I went, here's 1 to 2, which were invariant. The third discrimination is non-invariant, so I had to write that one separate. 4 to 7 were invariant. And then the same pattern here, 1 to 2 were invariant, 3 was different, 4 to 7 were non-invariant, and so forth. And here's the output that I got, and you can see that it matches what I did in in Excel, very close, which I calculated these things manually. And that I used to make this picture instead, which I think is easier to work with. Note that the pattern is the same. We have dashed lines that are lower for the women than the men, because B values are still scaled so that lower values are easier and higher values are more difficult. But now, rather than the y-axis giving you the probit of the lower category when theta is 0, this y-axis tells you how much theta you need to move to the next category. So if I go to this one right here, to move from can't do it at all to at least can do it sometimes, women only need a theta of minus 1.4-ish, whereas men need a theta of minus 1.2-ish. Or if I look at the green one, there's a bigger difference here. To say, yes, I can cook, takes a theta of about -1 in women, but a theta of minus 0.25 in men. So it takes more latent ability in men to have a 50-50 shot at crossing that threshold than it does in women. So I like the B's better because it tells you how much you need in each group. So it's still in the same latent scale, but I think it's a little bit easier to work with. The only thing to keep in mind is that the variance is only 1 in men, whereas it's less than 1 in women. So either way, if you want to talk about them in thresholds or B values, the idea is that these factor mean differences are only referring to some of the items. So are women less able than men? Yes, except when it comes to cooking. That's not creating the factor mean difference anymore because we let those thresholds go. And the same is true for some of the thresholds for housework and bed making. Those are no longer allowed to contribute to factor mean differences because they're estimated separately in each group. So where this gets tricky in practice is how many of these things can you have be different and still talk about the latent factor as being different between the groups. It's the latent factor except for all of these things that have gender-specific differences in addition to the latent factor. So, and words. Lots of words this time, as it were. So, put the picture back up. Questions? Yes, sir. I don't have to do that. I think in this case I did do it, just didn't show the code because you'd have to go backwards in terms of the order of the estimation. But I think I have a reference to it. I saw it just a second. Here. Right here. Yeah. So in that case, you have to go, so it's like metric against configural, and then you would have scalar against metric. In order to have metric A versus metric B, then you have to stop and re-estimate the same model with a different comparison, because metric A is being compared against configural, and metric B is compared against configural, so you'd have to re-estimate metric A versus metric B. Yeah, it's the order constraint is a pain in the ass, but yes. It's easier to do that when I just have a spreadsheet and I can do them all at once. But yeah, if you wanted to know if you're heading in the right direction by freeing something, then yes, you would go back to the more constrained model and see if it made it better. Yep. Now the node I was going to tell you about. Where did it go? That's a good place to end on. One of my most popular random people emailing me questions. This note at the bottom here. So M+ version 7 and above has introduced an automated procedure by which to do all of this. You type in your factor model, and there's an option, I think, under analysis that's like configural, metric, and scalar, and it will fit all of those constrained models and spit the output back to you. Cool, huh? That'd be nice. Why did we spend like 3 weeks on this or whatever when you can just do that automatically? Here's why. Because if it fails, when it fails, there's no automated procedure to figure out where your partial invariance lies. So then you have to go back to this anyway. The other reason is that the way they do it in terms of IFA, I disagree with theoretically. What they do when they get to scalar is because the residual variances are able to be estimated in the alternative group at that point, they put the scalar constraints on and simultaneously free the residual variances. So they're both adding things and taking things away in one step. And to me, I'm like, no, that doesn't make any sense. So I prefer to do it by hand so that I know what I'm testing rather than adding things and subtracting things at the same time, which to me makes them non-nested. And as I note here, reasonable people may disagree. So if you try to go through their automated procedures, if you were to have these data, I haven't shared the data with you because they're not mine to share, but if you had some, you would end up potentially with a different answer than what they spit out. But there's a reason for that. So, last but not least, if you want to do invariance testing using ML, the code looks different, and so I wanted you to have an example of that, although I'm not going to make you do it. For reasons that are unclear to me, if you wanted to fit the same IFA model using full information maximum likelihood instead, you're not allowed to use their multiple group setup. Instead, you have to pretend that it's a latent class model. Do you know what latent class models are? They're voodoo also, but it's where you're trying to find hidden groups, and it's all bullshit and stuff. Sometimes it's called mixture models. But anyway, they have this trick in here where you can say it's a known class. It's not latent. You don't have to find it. I have a variable that says what it is. So you use the known class option to denote your group, and then you can borrow their mixture model code to do the rest of it. And so you have this thing called an overall model that corresponds to what we used to just call model. And then for every alternative group, rather than saying like model men or model women or something, you do this %sign group #2% thing. I couldn't make this up if I tried, but this is the code that you would use for mixture models normally. In this case, it's a known mixture that's identified by the grouping variable. So the setup for this looks a little bit different. Because this is likelihood-based, you would end up doing -2 log likelihood comparisons to figure out your steps of invariance. However, because there is no covariance matrix to come back to, there's no voodoo to help you in terms of figuring out where you went wrong for partial invariance. So it is more cumbersome to use this method. This is where other existing IRT programs that are designed to test diff directly will do so much more efficiently, and will go through every possible permutation of testing items to be invariant or non-invariant. So I'd recommend looking into those if you're in this situation. So, ta-da! Questions? Yes, sir. Depends on the software. If it could be either. So you have to look in the documentation. It's either an intercept, a threshold, or a difficulty. One of the three. Other questions? All right, then here's the story just to recap. No class next week. Homework 5 is due by Friday night through Blackboard. Let me know if you run into problems. Jihong has office hours tomorrow. We have office hours today if you need access to M+. Lecture 8 and example stuff will all be moved until the Monday after break. Quiz 6 will be due that Wednesday. That way we'll have a chance to cover some new stuff by then. And homework 6, which will be over Invariance, is not ready yet. It will be ready shortly. I'll let you know. And that will be due the next Monday. So we're getting to the end, folks. All right. So have a good break. Take care of yourselves, and I will see you in a little while. How's that? Office hours start now.